Hello everyone! In this class, we will continue to learn about the extremum, maximum, and minimum values of functions. In our previous lessons, we learned how to use derivatives to find the extrema of a function. Let's review how to find the extrema of a function. Generally, we can find the extrema of the function y equals fx by following these steps. First, we need to determine the domain of the function. Second, we need to find the zeros of the derivative. Third, we divide the domain of the function fx into several intervals using the zeros of the derivative. We then list the signs of the derivative in each interval. From this, we can deduce the monotonicity of the function y equals fx within its domain. Finally, we can find the extrema of the function. We also know that extrema reflect the local properties of a function near a certain point, not its global properties within its domain. That is, if x0 is a local maximum or minimum point of the function y equal to fx, then why can't we find a value larger or smaller than fx0 near x equal to x0? However, when solving practical problems or studying the properties of functions, we are often more concerned with which value of the function is largest and smallest within a certain interval. When discussing the maximum and minimum values of functions, let's review the definitions of maximum and minimum values. Generally, let the domain of function y equal to fx be I, if there exists a real number m that satisfies these two conditions. Firstly, all x belonging to I have fx less than or equal to m. Secondly, there exists x0 belonging to I, such that fx0 equals m. Therefore, we refer to m as the maximum value of the function y equal to fx. It should be noted that both conditions for the maximum value are indispensable. Similarly, for the minimum value of a function, its definition is to set the domain of function y equal to fx as I. Firstly, if there exists a real number m that satisfies, firstly, all x belonging to I have fx greater than or equal to m. Secondly, there exists x0 belonging to I, such that fx0 equals m. Then we call m the minimum value of function y equal to fx. The maximum and minimum values of a function are the overall properties of the function. If x0 is the maximum or minimum point on a certain interval where function y equals fx, then fx0 is not less than or greater than the value of all functions on this interval where function y equals fx. The overall and local properties of a function are closely related. When finding the maximum and minimum values of a function, one can first examine its extremum. The following figure shows the graph of the function y equal to fx, where x belongs to the closed interval from a to b. Can you find its minimum and maximum values? Observing images is not difficult for us to obtain. fx1, fx3, and fx5 are the minimum values of the function y equal to fx. fx2, x4, and fx6 are functions where y equals the maximum value of fx. Can you find the minimum and maximum values of the function y equal to fx in the interval a to b? The vertical axis of the lowest point of the function graph corresponding to the minimum value of the function, and the maximum value of the function corresponds to the vertical axis of the highest point in the function graph. Therefore, we can see from the graph, the function y is equal to fx. In the interval a to b, its minimum value is fx3 and its maximum value is fa. We can observe more function graphs for research. In the following two images, observe the function y on the interval from a to b, which is equal to fx and y is equal to gx. Do they have a maximum and minimum value on a to b? If so, what are the maximum and minimum values? We can observe this image to know the function y is equal to fx and monotonically increases over the interval a to b. When x equals a, fa is the minimum value of the function. When x equals b, fb is the maximum value of the function. And observe the graph where function y equals gx. Increase in some intervals and decrease in some intervals. From the entire image, we can find the highest and lowest points of the image. So correspondingly, it can be known that the maximum value of the function is fx3 and the minimum value is f4. From the above analysis, we can draw the following conclusion. If the graph of function y equals fx on interval a to b is a continuous curve, please note that this interval is a closed interval, so we can conclude that it must have a maximum and a minimum value. So, what are the differences and connections between the maximum, minimum, and extreme values of a function? The difference between maximum, minimum, and extremum is that extremum is a local property of a function, while maximum minimum is a global property of the function. The second difference is that functions can have multiple maximum and minimum values. and the maximum or minimum value of the function is unique. Everyone can observe this picture. From the function graph, we can know that the maximum values of the function are fx2, fx4, and fx6. The minimum values of the function are fx1, fx3, and fx5. It's not unique, but the function y is equal to fx, and in this interval, its maximum value corresponds to the vertical axis of the highest point of the image, which is fa. The vertical axis of the lowest point of the function image corresponding to the minimum value is fx3. The maximum and minimum values of a function are unique. Thirdly, the maximum value of a function may not necessarily be greater than its minimum value. The minimum value of a function is not necessarily smaller than the maximum value. For example, let's still observe this picture. We can observe that the minimum value fx1 of the function is greater than the maximum value fx4 of the function. However, the maximum value of a function is generally greater than its minimum value, except for constant functions, because for a constant function, both its maximum and minimum values are equal to this constant. Fourthly, since the extremum of a function is a local property, it cannot be taken at the endpoints of the interval. The maximum or minimum value of the function can be obtained at the checkpoint. For example, the maximum values of the function we just talked about are fx2, fx4, fx6, and the minimum values are fx1, fx3, fx5. They didn't get it at the endpoint, and the maximum value of the function is fa, which reaches its maximum value at the endpoint. What I just talked about is the difference between the maximum and extreme values. The relationship between the maximum and minimum values of a function and its extremum is that sometimes the maximum and minimum values of a function are also its extremum. For example, we can observe the graph where the function y equals gx. From the image, it can be inferred that fx3 is the maximum value of the function. At the same time, it is also the maximum value of the function over the entire interval. fx4 is the minimum value of the function, and also the minimum value of the function over the entire interval. So on this basis, let's ask, how to find the maximum and minimum values of a function in the interval a to b. We can define the maximum, minimum, and extreme values of a function. We can compare the extreme values of function y equal to fx with the function values of the endpoints. So the maximum is the maximum value of the function, and the minimum is the minimum value of the function. In this way, we can calculate the maximum and minimum values of the function. Now let's take a look at this example. Find the function fx equal to 1/3 of the cube of x minus 4x plus 4, and the maximum and minimum values on this closed interval. So according to the previous explanation, we can first find the extremum of the function and compare it with the endpoint values of the interval, namely f0 and f3. So the largest one is the maximum value of the function, and the smallest one is the minimum value of the function. In the previous class, we have already determined the extremum of this function. Let's roughly demonstrate the specific process. Firstly, determine that the domain of the function is from -infinity to +infinity. According to the analytical expression of the function, its derivative can be obtained as x squared minus 4, and finally decomposed into x plus 2 multiplied by x minus 2. By making the derivative equal to 0, we can solve for x being -2 or x being equal to 2. So when x changes, the derivative function and its variation can be displayed in a table. From this table, we can see that when x is -2, fx has a maximum value, and the maximum value is f, -2 equals 28/3. When x equals 2, fx has a minimum value, and the minimum value is f2, which is equal to the -4/3. So everyone should pay attention below. Since we require the function y to be equal to fx, the maximum and minimum values on the closed interval 0 to 3. Not within this range. In the range of 0 to 3, we need to pay special attention to this minimum value, where f2 is equal to the -4/3. We note that the function values f0 at the endpoints of the interval are 4 and f3 is 1. Compare the minimum value just now with him, so we can find that the function fx is equal to 1/3 of x squared minus 4x plus 4. Its maximum value on this closed interval is 4. The condition for taking the maximum value is when x equals 0, and the minimum value is -4/3. When x equals 2, the function takes this minimum value. It is also easy to draw the graph of this function on the closed interval 0 to 3. It can be seen that its minimum value is -4/3, and its maximum value is 4. So through this example, we can see that there are two steps to finding the maximum and minimum values of the function y equal to fx on this closed interval a to b. The first step is to find the extremum of the function y equal to fx in the interval a to b. The second step is to compare the extreme values of function y equal to fx with the function values at the endpoints, namely fa and fb. The largest number is the maximum value, and the smallest number is the minimum value. Let's take a look at this example. When x is greater than 0, it is proven that subtracting 1 of x from 1 is less than or equal to ln x. We can draw y equal to 1 minus 1 of x, where x is greater than 0, and its image is C1. We can also draw y equal to ln x. Its image is C2. From this image, we can obtain the geometric meaning of this inequality, which is that, except for points 1 and 0, the curve C1 and y are equal to 1 minus 1 of x. Its part on the right side of the y-axis should be located below the curve C2, which is y equals to ln x. So how to prove it? We can convert inequality 1 minus 1 of x less than or equal to ln x into 1 minus 1 plus ln x greater than or equal to 0. Furthermore, we can use a constructor to set fx to be equal to 1 of x minus 1 plus ln x. So we can transform the inequality into proving that the minimum value of function fx in the interval from 0 to positive infinity is greater than or equal to 0. We convert inequality 1 minus 1 of x to less than or equal to ln x, which is equal to the sum of 1 of x minus 1 and ln x being greater than or equal to 0. Let fx be equal to 1 of x minus 1 plus ln x. So we can get that its derivative is negative x squared plus x squared. We can divide it by x squared and subtract 1 from it. Furthermore, by making the derivative equal to 0, we obtain x equal to 1. We also have a table to represent the derivative function and its changes when x changes. In this table, when x is in the interval of 0 to 1, the derivative is negative and the function monotonically decreases. When x belongs to 1 to positive infinity, the derivative is positive and the function monotonically increases. When x is equal to 1, its derivative value is 0, and f1 can be calculated to be 0 as well. It is the minimum value of a numerical function and also the minimum value of a function. Therefore, we can conclude that when x equals 1, fx reaches its minimum value. So, fx is greater than or equal to f1, and f1 is equal to 0. So we can get x divided by 1 minus 1 plus ln x greater than or equal to 0. We have proven that when x is greater than 0, 1 minus 1 of x is less than or equal to x. Through this example, we can obtain the maximum and minimum values of the function on a certain interval. We can also adopt the following method. The first step is to discuss the monotonicity of the function y equal to fx on a given interval. The second step is to determine the maximum and minimum values of the function based on its monotonicity. We make the graph of function y equal to ln x and function y equal to x minus 1. It can be observed that on the right side of the outer axis, except for point 1, 0, curve C3, y is equal to the portion on the right side of the y-axis where x minus 1. To be located above curve C2, y is equal to ln x. Therefore, we can speculate that when x is greater than 0, we can prove that if x is less than or equal to x minus 1. Next, let's summarize the learning content of this lesson. We learned how to use derivatives to find the maximum and minimum values of a function. Generally speaking, we have two methods. The first method is to use derivatives to find the extremum of a function. Further, compare the extreme values of the function with the function values at the endpoints of the interval. Thus, the maximum and minimum values of the function can be determined. It is worth noting that this method is suitable for finding the maximum and minimum values of a function on a closed interval. The second method is to use derivatives to study the monotonicity of functions. Furthermore, we can utilize the monotonicity of a function to determine its maximum and minimum values. The commonality between these two methods is the use of derivatives to study the monotonicity of functions. Everyone should pay attention to the instrumental role of derivatives in this process. That's all for this class. Goodbye, everyone.